Hello, everybody. This is Sunday. It's May 15th, and we are moving into the second week of our online astronomy course. And I'm really excited because this is Sunday, and this is the night of the total lunar eclipse. I hope it's not going to be cloudy, but the forecast is not looking good. If I get a good view and I get a good picture of it, I will post that photo. I'll post it below the link for this video. And in astronomy news, something really spectacular has happened, and that is that we've just had our first look at the supermassive black hole that is at the center of our Milky Way galaxy. And here it is. It looks like this. Now, when you take a picture of a black hole, of course, you can't take a picture of the black hole itself. It doesn't give off any light. That's what a black hole is. But you can image the light that is bent around the black hole by its immense gravity. And so what you're seeing is the light from all of the stars that are in the vicinity of this supermassive black hole at the center of our Milky Way galaxy. And at the center is a shadow of our black hole. And this is the first time we know for sure that the object at the center of our Milky Way galaxy is a supermassive black hole. How massive? It has a mass of about 4 million suns. And it's huge. If I go from one side to the other, it's about 24 million kilometers. So it's a huge object. It dominates its local environment, but still its mass is only a small fraction of that of the Milky Way. And the Milky Way is hugely larger than the black hole itself. And you'll be finding more about our Milky Way and the black hole at the center of it when we get to studying the Milky Way in one of our later modules. And in fact, you can see exactly where that supermassive black hole is. If you're looking over my shoulder here, you can see the center of our galaxy right about there. And that black hole is right about, I would say right here, right there is where the center of our galaxy is, and it is where that supermassive black hole is found. Module 2 is all about the early efforts at understanding the night sky, early astronomy. And by early astronomy, I mean something that took place before the invention of the telescope for the most part. And, who were the first astronomers? Well, they were the first people to look up at the sky and wonder about what they were seeing. And these were men and women who probably lived in caves somewhere. We have elaborate cave drawings in France that we know these people certainly did wonder about their environment and about the nature of the physical world. But the first written records of astronomy stem from Mesopotamia and ancient Babylon. And those records, we find star catalogs, people recording where the stars were in the sky. They noticed the basic rhythms of the sky. They watched as objects would rise in the east and move across the sky and set in the west. And this is a good time to get our orientation here. You're facing the screen as you watch this, and you're watching the Milky Way, which is in the south. So right now, watching the screen, it's like you're facing south. Now, if you stretch out, if you're facing south and you stretch out your left arm, go ahead and do it. You're pointing toward the east. That means the east is to the left side of the screen over there. And if you stretch out your right arm, facing south, you're pointing to the west. And so that means the west is over to the right side of the screen. And so we can talk about how all objects rise in the east, move across the sky, and set in the west. And that goes for stars do that. The moon does that. The planets do that. And why is that? Well, today we know that that's because Earth is spinning on its axis. And it's like if you were sitting in a chair that could spin around, if you spin yourself around, it looks like the room is moving around you. When really it's not the room that's moving, it's you who's spinning. And as we watch the stars come up in the east and set in the west, we know that's really because Earth is spinning. But if we take away that motion, the patterns made by the stars don't change. They're pretty much the same all the time. If I were to come out this year or at the same time next year or at the same time in 10, 100, or 1,000 years, the sky would still look like it does today. Now, even the ancient people knew that the moon orbits. The Earth takes about a month to go around. And in the last module, you learned all about the phases of the moon that the moon goes through over the course of one orbit around Earth. And you also know that from night to night, the moon moves from west to east. So things just move in the sky eastward from night to night. And that's not due to Earth's rotation. That is just due to the moon's orbiting Earth. And the planets do much the same thing, but not exactly. And this is what drove Greek astronomers absolutely nuts, because they would watch the planets from night to night. And there are two planets in this picture. One is right here, and that's Mars, and the other one's over to the right of it, and that's Saturn. But for instance, let's just focus on Mars. From one night to the next night, Mars might move from here to here against the distant background stars. And the next night, it might move from here to here. And the next night from here to here, and so on as it moves across the sky. And same thing for Saturn. Saturn might start out here, the next night it's here, next night it's here, the next night it's here, and so on. So the planets are generally moving eastward. That's their regular motion. But sometimes Mars, Saturn, all the planets do this. They'll be going eastward from night to night, from here to here to here to here to here. And then suddenly they'll be moving westward for a bit. They'll go from here to here, backwards in the sky. And that backwards motion is called retrograde motion. Retro meaning against, and so it's against the flow of its normal motion. And then it resumes its normal eastward motion again from night to night against the distant background stars. Now, that was so hard for the ancient Greeks to understand, because the ancient Greeks believed that everything moved in circles at a constant speed. Why circles? Circles are the perfect shape. So why would the universe choose anything else than circles? And so everything had to move in circles. The moon moved in circles around Earth. They thought the sun moved in circles around the Earth. So they lived in an Earth-centered solar system, in a geocentric solar system, geo-Earth, centric-centered. And this geocentric system was part of their lives. And they believed the planets would move around Earth, always moving to the east, supposedly, always moving to the east. But then why would they back up? How is that consistent with always moving in the same direction around a circle? Oh, that puzzled them. And in fact, the Greek word for planet, the Greek word planet is a Greek word, and it comes from the Greek word for wanderer, because the planets would wander across the night sky sometime, from night to night to night. and their motion was different than that of the moon and other things that would move only eastward. And so the word planet just by itself tells you there's something different about these objects. So how to understand this? And it's not that the Greeks, weren't brilliant astronomers, because they were. A man named Eratosthenes figured out the size of Earth by studying the shadows cast by the sun. And you're going to use a method, at least you'll, if you do one of the optional observing projects, you can use Eratosthenes' method, because Eratosthenes used this method to measure the size of the Earth, and you can do that too. So they were certainly capable astronomers, but this just drove them nuts. Why did the planets move backwards? Just using circles. And what they came up with is that maybe what's going on is that a planet moves in a small circle. That small circle is called an ellipse. So there's the planet moving around in a small circle. And at the same time, the center of that small circle moves around a larger circle. That larger circle goes all the way around the Earth. That larger circle is called the deferent. And so as the planet is moving around the epicycle, the center of that epicycle is going to move around the Earth and carry the epicycle along with it. And so just think about what that does. And here I'm going to move my hand from the west side of the screen, that's over on the right, over to the east side. And I'm going to have it going in a little circle. And watch what happens as my hand smoothly moves across. I'm going to try that with my other hand and start my other hand over here just so I can move it across a little bit more smoothly. So here's my fingers going in a circle. And what I want you to do is you can imagine that the planet is right where my fingertips are meeting here. And what I want you to do is to point at my fingers. And I'll move them slowly so you can see them. There we go, try to get them a little closer to me. I'm just going to move my fingers in a circle while my hand goes across the screen. So here we go. So first of all, it's just the planet moving around the epicycle like this. So now what happens is my hand moves across the screen at the same time. So here we go. So my hand's going to go across the screen at the same time. So at the same time, I move my arm across the screen, which carried my hand and the planet along. I hope that you could see that what would happen is that my fingers moved across, but then they went backward a little bit, moved across and went backward a little bit, moved across and went backward a little bit, and so on. And using this system of a large circle called the deferent, and on that circle moved a smaller circle called the epicycle, and the planet moved around the epicycle. But that allowed the planet sometimes to move backwards, that is westward in retrograde motion. There's a video about this, so please watch the video and try to imagine how that works. This is a confusing topic, and it just shows the length that the Greeks went to trying to understand the motions of the heavens. And it's completely wrong. I mean, there are no epicycles, there are no deferents. Right? This is a model of how the world worked for the ancient Greeks. And by a model, I just mean it's a system that reproduces the observations that they saw, the observations of the changing movement of the planets. And that tradition of making models still exists in astronomy today. We still make models of things in order to understand them. But in the case of the Greeks, you have to test your models against the observations. And the models were very successful. The Greek models lasted for about 1,000 years. So for 1,000 years, people believed in epicycles and deference. And if you've ever been to Europe and have been to the center of a town, and at the center of old towns, you'll often find a clock. And what they usually have is the Earth on one of the hands going, the sun on one of the hands going around the Earth, which is at the center of the clock face. And so this geocentric solar system was ingrained in what everybody believed. And it wasn't until a man named Nicholas Copernicus came along. And he finally said, you know, this system of epicycles and deference is just too complicated. It all is a lot easier if everything moves around the sun. And so he advocated for the first time a heliocentric solar system. Helios, the Greek sun god, named after him. So everything orbits the sun, except for the moon, which orbits Earth. So the planets orbit the sun, just like we do on Earth. So how does this explain retrograde motion? Well, have you ever been just walking around maybe a track or walking around a circular path? And suppose that you there's somebody else walking along, but you're faster than they are. So you pass them by, And as you pass them by for an instant, it looks like they are moving backwards. You know they're really moving forward, but from your point of view, because they're in front of you, and then as they pass by, they move to being in back of you, it looks like they're moving backwards for a second. And that's what causes retrograde motion. As Earth passes, for instance, the more slowly moving Mars, it looks like Mars is moving backwards in the sky for a short period of time. And again, watch that video on retrograde motion, and that'll explain how the heliocentric model of the solar system, which is the correct one, works. So Copernicus still had everything moving in circles, and those circles were centered on the sun. That's got it half right. Soon after Copernicus died, Copernicus, his great book on the motion of the planets, written by Copernicus, was published on the day he died. But soon after that, another man named Johannes Kepler really wanted to know how the heavens moved. And he inherited some very, very precise calculations by a Dutch astronomer named Tycho Brahe. Brahe was the greatest naked eye astronomer of his time before the invention of the telescope. And Copernicus inherited Brahe's observations, and he used them to try to figure out what that said about the motion of the planets. And he tried to fit the orbit of Mars to a circle, and he couldn't do it. It was close, but it was greater, but the discrepancy was greater than the errors of Tycho Brahe's observations. And so, Kepler, instead of saying, oh, that's good enough, instead of that, he actually said, nope, we're going to throw all that out. And he didn't say I'm going to find 3 laws, but he did find 3 laws of planetary motion. And you'll learn about those in this module. Basically, it says that the planets don't move in circles. They move in an oval path called an ellipse. Now, a circle is just a special ellipse, but all the planets move in elliptical orbits. And asteroids and comets and everything that orbits everything else because of gravity moves in an ellipse. Kepler's second law talks about how fast a planet moves around the sun? Where does it go fastest? Where does it go slowest? And his third law talks about how long it takes different planets to orbit the sun. So Kepler's laws of planetary motion were a triumph, but they were based on observation. Why did Kepler's laws work? Why is the universe arranged this way? And we'll find out in the next module that it's Isaac Newton and his laws of motion and gravity that completely explain Kepler's laws, and it's what astronomers use today to understand the motions of the solar system. But around the time of Kepler, in fact, on the day Isaac Newton was born, another man died, and that man was Galileo. And Galileo, although he didn't invent the telescope, perfected the first telescope. And he was the first person to turn telescopes skyward. And he discovered craters on the moon. Oh my gosh, the moon is not an unblemished sphere, a perfect sphere, you know, the way Dogma had it. No, it has craters and mountains on it. He discovered countless stars that you can't see with the naked eye through his telescope. He discovered moons of Jupiter. So, oh my gosh, Earth isn't the center of all things because here's moons orbiting Jupiter. These are revolutionary ideas. But as I said, in the year Galileo died, Newton was born. And we'll pick up that part of the story in the next module. So, hope you enjoyed learning about this. I think this is just great stuff, learning about where astronomy came from. I mean, ultimately, it was developed by people wondering about how things moved. And I hope you do enjoy learning about that. Now, before we go, I do want to put Stellarium up here for a second. So let me do that. Here's Stellarium. And this is what the sky is going to look like on Tuesday evening. And we're looking here to the south. So again, east is on the left side of the screen, west is on the right side of the screen. And here is the moon in the southeast. And it's right beside this reddish star. And the name of that reddish star is Antares. Antares. The name comes from the Greek, as do many things, means anti-Aries. Anti meaning a rival to, Aries meaning Mars. Because just like Mars looked reddish in the sky, Antares looks reddish in the sky. So the Greeks imagined that these were two rivals, Antares, the rival to Aries. Now, Antares is about 550 light years away. And the main reason I wanted to tell you about it, and it's easy to find because the moon is right next to it. On this night, on Tuesday night, the moon's right next to Antares. The size of Antares is about, oh my gosh, 680 times the size of our sun. If Antares is where the sun is right now, the surface of Antares would extend past the orbit of Mars. And Mercury, Venus, Earth, and Mars would be completely swallowed up. This is a red supergiant star, and you'll be learning about them. Excuse me, learning about them in a coming module. So just giving you some previews ahead here. I hope you do enjoy learning about the history of astronomy. Always, if you have any questions, you can post something in the discussions. I was slow getting into discussions this week because just a busy week, but I will be responsive to discussions. Send me an email. We can set up a Zoom meeting or meet in my office, whatever works for you. So have a great week, and I will look forward to seeing you next week. And I hope it's clear tonight for that eclipse. So until then, I will see you next time. Bye-bye.